Hey, you go to the last page of your packet. Again, I want to just make sure that we know what to expect on the upcoming test. So you're going to see a problem similar to the one that we did in class on Friday, where we have to do curve sketching, use the first derivative test to create your sine line, find relative max, relative min, use the second derivative function to find your points of inflection, but no sketching graphs. Okay, so for curve sketching problem, I'm just going to ask you for information related to first and second derivative sine line, but I'm not going to ask you to sketch your graph. There will be a particle motion problem. We're going to see. We did the one in class yesterday, and we're also going to work through one of those problems today. The quiz that you just took involved problems with expanding log terms. Seems like most of us were pretty good with that. Still finishing grading our quiz, but it's like we're able to apply those expansion properties before we jump into our derivative rule. The four new rules that we're responsible for involving base E and base A, logs and exponentials. Knowing when to apply product rule, quotient rule, and chain rule for derivatives. Finding equation of tangent line, we did that yesterday as well. Implicit differentiation, we did that yesterday. We'll do one again today. Log differentiation, we didn't start that yesterday, so I want us to start that problem. This is the problem where we don't have a rule available to us, and we have to use logs to help us get the equation into a different form so that we can actually find the derivative. And then also finding derivative of inverse at a point. When we did this in class, you guys were pretty good with it, so hopefully that continues. We can just review that. And we're just going to cycle through these concepts over the course of these next days leading up to the test. And again, no calculators on this test. Okay, no calculators on this test. Okay, so go to page 2 in your packet. Okay, did we finish number 4? I think we did, right?
Yeah, we did.
We did, okay. Okay, so let's look at number 5. Okay, so number 5 says find dy dx if y is equal to the cube root of 2 plus 5x cubed raised to the x power. Let's rewrite this problem first to kind of get a little, get this looking without, see what it looks like without the radical. So what would that look like? Parentheses, close, raised to the what? What's the power? Yeah, x is in the numerator of my exponent. 3 is in the denominator of my exponent. So x over 3. Okay, so there's something that I want us to realize about this type of an expression. This is in the form of a variable base, because there's a variable in my base expression, raised to the variable exponent. Okay, variable base raised to a variable exponent. And I want us to realize that we don't have a rule that can handle this sort of a form. Okay? We don't have a rule that can handle this form, so we have to get this to a different form. If I have a variable raised to a constant, that's like x squared, right? We have a rule for that. We can do variable raised to a constant, that's power rule. What if it was a constant raised to a variable? That's a to the u, right? Or e to the u, depending on what your base is. Right, but we don't have a variable raised to a variable. So we got to first recognize that this is a variable raised to a variable. Okay, you got a variable in your base, you got a variable in your exponent. Let me rewrite this. It helps make it 1/3 x. So that eventually when it comes down, it just will feel like it's more ready for whatever rule you want to go to. So because we can't because we can't work with that exponent in the place that it is right now, we want it to be put into a different location. So what do you think we can do to this problem to allow that exponent to move? We can introduce something into the problem. Yeah, introduce natural log, right? We have all those log properties that allows exponents to freely move. So this is called a log differentiation problem. We use log differentiation when we're stuck, when the problem doesn't allow us to identify a rule, and we want the problem to look a little differently. Okay. So we'll take the natural log of both sides. Okay. What can we do next? What can we do with that exponent? Move to the front, right? Now, when you move it, you haven't done anything derivative wise. All you've done is you've put it in a new location that will help us identify a rule from here. So now that the 1/3 x is in front, we don't have to worry about that variable exponent. It's now brought down to the base level. So now we're ready to begin thinking about our derivative process here. What's going to have to happen on the left side? There's a little bit of what? Is that y by itself? So anytime you have y mixed into the equation, we have to do a little bit of what? Implicit, right? This is where we have to kind of collect our dy dx's, right? But there's only one y there, so we know there's only one dy dx. And then for our derivative process, what needs to happen on the right side? Product rule, right? We can't just rely on one rule, and we can't just say, oh, power rule and log rule. That there's a multiplication between those two terms, and we got to go through product rule. Let's find our derivative. Natural log of y becomes what? U prime over u, right? So what's u prime over u? 1 over y, okay. But we just took y's derivative, so we also need times dy dx. Okay. Product rule, f prime g plus f g prime. Let's go through each term here. F prime becomes it's 1/3 x become third. Okay. G function, no changes. Back to f. Okay, g prime. How do I take the derivative of natural log of 2 plus 5x cubed? U prime over u, right? So 15x squared. And we can clean up that expression a little bit on the right side. I'm not going to ask you to find common denominators, but anytime that we can do a little bit of cleanup, we can do that on our with the next step. But let's think about the big picture here. We're close to the end. What are we trying to solve for? About the x, right? We're trying to find the derivative, okay? So what's the last thing we need to move? On the y. Yeah, so when that 1 over y moves over to the right side, where what does it become? It's in the denominator right now, so if I divide by a fraction, the same thing as multiplying by the reciprocal, right? So it's going to be a y in the numerator on the other side. I'm going to merge these two fractions together here. I can multiply them. The 15 and 3 can reduce to be just 5. And then the x and x squared can become x cubed. Okay, we're almost there. One final thing to do. We can make a replacement, right? So what can we replace? Yeah. With what? With the original equation, okay? So we have a function. So if we have a function, then if we find our derivative should not have any y's in it. So the y is there as kind of a temporary variable, but we want to bring our derivative back in terms of just one variable, just in terms of x. So when you move that y over, make sure you bring back your original variable, x. Okay, with log differentiation, your derivative will just look messy, but that's fine. It's usually a little bit longer, but you're not expected to have to do a whole lot of cleanup. Okay, any questions here? Okay, so I want to make sure that when we see this problem on the test, that we can recognize the need for log differentiation is when you see that variable raised to a variable, right? If you see this setup, you know that you're kind of stuck not having a rule to work with. So we got to have some help to kind of make that equation look a different way. So we introduce logs into the problem, or natural logs into the problem. That exponent is now free to move. Once that exponent comes down, then we have product rule available for us to find the derivative, and left side a little bit of implicit. Okay, move the y over and make sure you replace the y back in terms of x. This will be a test question. So any questions at this time? We'll see a few more of this before Tuesday, but I want to make sure at this time that you're comfortable recognizing the need for log differentiation and understanding the steps leading to the end. Yeah.
How many questions will be on the test?
The test is about like 6 or 7 questions. It's going to be like 2, 1 particle motion. That's an extended problem. 1 curve sketching, that's a problem, and then you have these small problems, 1 of each type. Okay. Okay. let me have us go to. I want to do a derivative of an inverse at a point. We haven't seen that in a while. So in your packet, I have it in the, some further along in the packet. You can go to page 22. I want to make sure we still remember these steps so I can remind you of these steps. You'll see a problem like this on your test as well. Page 22. Okay, so this problem here, find the derivative of an inverse at a point given the original function. So I like to use this chart to kind of help me gather what I need to do. So I'm basically going to be starting with my end goal, and I'm going to be working around this chart here. And as I gather information, eventually, once I come around full circle, I'll be able to have enough information to make my conclusion. So I'm trying to find the derivative of inverse at a point. That x value is for my inverse. So I'm going to say the derivative of my inverse at 2 is the unknown. That's my end goal. Okay. Now for my first two, my top row here, I'm going to show the relationship between a function and its inverse in terms of their order pair. Their order pair will be flip-flopped. Okay. And then on the second row here, at their corresponding points, the slope of the function and its inverse at their respective corresponding points, the slope values will also have a specific relationship with each other. Okay, so and then they're going to be reciprocal relationships. Okay, but just from this information alone, I can start filling some of this table in, because I know that for my order pair, x is my 2 is the x value of my inverse, but on the function side of things, 2 is the what? The y value. Oops, sorry. F of parentheses is equal to 2. Right, so I know that there is that flip-flop relationship. We're not going to do anything on the inverse side of things. We're doing everything on the function side of things. And then once we gather enough information, we can take whatever we have and make a conclusion about the inverse. Okay. So I know that the y value of my function is 2. How can I take my next step? Yeah. So I'm trying to find the x value of my original function, but I only have the y value. So we have to make sure we understand that this 2 doesn't insert itself into the x. The 2 is going to be the y value of my function. Because we're trying to work backwards here to figure out the x value so that we can make further conclusions. Okay, so 2 is equal to. All right, I'll set everything equal to 0 to help me solve for x a little bit easier. But this is not going to be something that we can factor, right? If I subtract 2 from both sides, I get -2, -2 minus 1 is -3. So because I can't factor, I have to do a little bit of guess and check. But the number will be easy to find. Okay? It'll be a nice whole number close to 0. Right? So just begin testing through your numbers, test 0. If 0 doesn't work, try 1. If it doesn't work, try -1, then 2, then -2, and at most, you're going to have to go to 3 and -3. Okay, but after you test a couple of numbers, you should be able to arrive at your x value. So what x value will allow this equation to work? 1. So let's test it out. 1 cubed is 1. 2 times 1 is 2. 1 plus 2 is 3. 3 minus 3 is 0. So 1 is my x value. Now I can go back and fill in my order pair. I know my order pair for my function is 1, 2. On my inverse side of things, it must be 2, 1, just to kind of help me confirm that a function and inverse will always have flip-flop order pairs. Now, if I can gather my slope on my function side of things, then that number will lead me to the slope that I'm looking for on the inverse side of things. So I want to find f prime of 1, but before f prime of 1, I first have to find f prime of x, right? Let's find the derivative. Okay, so f prime easy power rule here, x cubed plus 2x becomes. What's the derivative? 3x squared plus 2. Now that I have my slope formula on my function side of things, I can find f prime of 1. What's my slope? Slope is 5, okay? So if the slope on my function side is 5, then the slope on my inverse side must be what? 1/5. That's what we're looking for. That's the answer that you're providing. Always just take the reciprocal. Don't try to change the sign. We do that for parallel and perpendicular lines, right? We take the opposite reciprocal, but not for this, okay? Your slope will both be the same sign, just one is a lot steeper than the other. Or one is steeper than the other. Okay, how do you guys feel about this? You'll see this on the test. Steps make sense. Okay. All right, good. Okay, so we've seen one of every type since last Friday. So now let's go back to review worksheet 2. And let's do a full particle motion problem. So this is on page 11. Okay, so for part A, it says the position of the particle moving on the x-axis is given by x of t. Show that velocity is equal to this. Okay, so this is what we're trying to arrive at. This is the answer. We just have to connect the dots from the beginning to position to velocity. So how can I get from position to velocity? Take the derivative, right? PVA, position, velocity, acceleration. And if I want to find the derivative of 2t over e to the t, what process would I go through? Quotient rule. Okay, so try that. Go through quotient rule, f prime g minus f g prime with your x of t. And then after you clean everything up, derivative, you should be able to arrive at v of t. So that's your goal. Your goal is to get to v of t. Okay, try that. Okay, f prime g minus f g prime all over g squared. So I want to clean that velocity function up so that I can get to what is presented under part A. What can I do to clean up that numerator? It's not like terms, right? I can't combine it, but what can I do? What do you notice about both these separate terms here? They both what? They share what?
E of t.
E to the t, okay. You can take e to the t out. I took out 2 as well, but either way, if I want to take out my greatest common factor, let's say I took out 2e to the t, then that means I'm dividing 2e to the t from both these terms. So if I divide my first term by my GCF, I'm left with just 1, because 2e to the t divided by 2e to the t is just 1. And my second term here, if I divide 2t to the t divided by 2e to the t, then I'm just left with t. And that will allow me to take out one of the t's, or one of the e to the t's, because e to the t squared is really just e to the t times e to the t. And then if I redistribute the 2 through, then I can make it look like what is presented for part A. So there's my velocity function. Okay, part B is asking you to find the acceleration function. So how can we get from velocity to acceleration? Derivative and do what again? Function rule. Okay, try that. Go through function rule again. And see if we can make it look like part B. Okay, f prime g minus f g prime all over g squared. Take my parentheses, distribute that through, try to clean that up a little bit. And then again, I'll try to factor out my GCF to see if I can clean up my expression. So once I distribute that through, I do have a couple of like terms there. Negative 2e to the t minus 2e to the t is negative 4e to the t. There's a GCF that I can, or common factor in my two numerator terms. I can factor a 2 and an e to the t from both terms. Divide them out. It's like 2e to the t is my common factor. I can take out one of them, one of the e to the t's from numerator and denominator, distribute the 2 through again, and I'm able to make it match my acceleration for part B. Okay, any questions so far? Okay, so now that we have our velocity and acceleration, we're gonna answer the rest based off of position, velocity, acceleration functions there. So for part C, it says, for what value of t is the particle at rest? So what do we use to determine where the particle is at rest? Velocity, right? Particle at rest is, what does that mean? That means velocity is what? 0. Okay, so I want to set velocity equal to 0. But my velocity has both the numerator and the denominator. So do I set them separately? Do I just look at the numerator? Do I look at just the denominator? What do you think? All right, it's just going to be the numerator. Right? Why not the denominator? Okay, if I set my denominator equal to 0, then I'm looking for when my velocity is undefined, right? That's different than 0. So 0 is just going to be the numerator of your velocity function, assuming that there's a denominator to choose from. I want my velocity 0, not velocity undefined. So solve for t. T equals what? 1. Okay. Okay, for what value found in part C, right? We found t equals 1. Is the particle located to the right or to the left of the origin? So we're looking for location. So what's going to be used to help us find location? Position, velocity, or acceleration? Position, right? So we can just find the location at t equals 1, and then see whether we get a positive or negative value, right? Positive means to the right of the origin, and negative means to the left of the origin. Okay, so we'll do x of 1. Okay, positive or negative?
Positive.
Positive, so we know that's to the right. Good.
Is that only needed for justification too?
Yep, we just say that's greater than 0. Therefore, this particle is to the right of the origin. Okay, for the same value found in part C, again, this is for t equals 1, is the velocity increasing or decreasing? So think back on your particle motion problems from chapter 2 and 3. How do we determine when the velocity is increasing or decreasing? What do we look at? Just acceleration, right? So if acceleration is positive, then velocity is increasing. When acceleration is negative, then velocity is decreasing. I know the tendency is you want to use velocity because you see the word velocity there, but that increasing, decreasing is changing it. It's talking about its rate of change. It's not talking about the velocity itself. So I'm going to insert 1 into my acceleration function. So acceleration is negative, therefore velocity is decreasing. At t equals 1. Let's cross out part F. I won't ask you about acceleration increasing, decreasing, because then it's asking about derivative of acceleration. Okay, let me reword this problem here. So, or change this problem for part F. For what value of t is acceleration equal to 0? Okay, so how can I find this?
Is acceleration equal to 0?
What part of acceleration?
The numerator.
Yep, numerator. I think that should help with part G. What is the velocity when the acceleration is 0. How can that help us for part G? Right. Do we know when acceleration is 0? Equals 2. So then what can we do with that information? Yeah, plug the velocity, right? It says what's the velocity, so. Okay, 2 minus 4 is -2, -2 over e squared. There's our velocity. Okay, at t equals 3, is the velocity of the particle increasing or decreasing? So same process, right? What do we do here? Into acceleration, yeah. I get a positive acceleration, therefore velocity is increasing. Part I, at t equals 3, is the speed of the particle increasing or decreasing. So how is this different? Yeah, how do we determine whether speed is increasing or decreasing? The jet's velocity? We got to do what? Compare signs between what? Velocity and acceleration. Yeah, so we need to figure out what is the velocity and acceleration at 3 and compare their signs, right? If they're both the same signs, then speed is what? Increasing, okay? But if one is positive and the other is negative, then decreasing speed, okay? Good. So we already have acceleration at 3 seconds. Let's find the velocity at 3 seconds. So I get a negative velocity, so therefore what can we conclude?
Decreasing.
Decreasing, yeah. Since velocity and acceleration have opposite signs, speed is decreasing at t equals 3. Okay, for part J, for what value of t is the particle located at the origin? So we're talking about location, so we're working with what? Position. So location at the origin means what? Means position is 0. So just replace 0 in for x of t and solve for t, right? And we're just going to be setting what equal to 0.
The original function.
Yeah, original function, but
The numerator.
numerator, yeah, numerator. We don't want to know when the position is undefined. We want to know when the position is 0. Okay. Let's look at page 12. Let's look at the top problem here. Number 2. I find dy dx for natural log of xy squared equals y squared minus 3x. Can you list out what process we have to involve here if I eventually want to find the derivative? Okay, implicit, good, because you see y's all over the place. What else? Product rule, yes, but is there a way to maybe avoid product rule for derivatives?
If you bring in an E.
Something else. Something else. Yeah. So anytime I see a messy natural log expression, think about expanding, right? If I can expand it, then my derivative process will be a lot more manageable rather than having to go through u prime over u and dealing with a product rule within my u prime over u. That's a bit messy. Okay, so go ahead and try that. You're gonna expand first. Once you expand, then we're gonna look to see if implicit can help us through, or we can collect our dy dx's through implicit. Okay, is there anything that we can do before our derivative step? Yeah, I can bring 2 down. It's not, it's, we can still work through, we can jump to derivative without it causing too much of an issue, because u prime over u is not too difficult with y squared, but this just feels a little bit easier if I can bring it down, but it's still manageable with it up. Okay, we're ready for our derivative. Everything should feel pretty easy here. There's no nested chain rules that we got to worry about. Just have to keep track of our dy dx's. Okay, so natural log of x becomes 2 natural log of y becomes 2 times u prime over u, so 1 over y. What else? dy dx. Y squared becomes 2y dy dx. 3x becomes 3. So we'll combine our put our dy dx terms together so that we can factor dy dx out. Factor out the dy dx. Divide the parentheses over. Now, something that I want us to be able to do is, well, on the AP exam, if you see this as multiple choice, it won't be presented like this. It'll be presented with the complex fraction resolved. So let's see if we can work our way to that point. So I need to find common denominators for my numerator and my denominator so I can eventually collapse these 2 fractions. So let's deal with the top first. What's my common denominator in my upper fraction here? X. Now, balance each of the fractions here. If there's no changes, I can just bring over my numerator. But if there is a change, I need to figure out what is different, right? So I'm missing a what from the denominator. Next, right? So I need to multiply the top by an x. Okay. What's my common denominator? My denominator is y. Okay. Balance the fractions out. 2, and this is missing a y, so I need to multiply the top by y as well. So 2y squared. So now I still have a complex fraction, but at least I've gotten it down to a fraction divided by a fraction. So I can do what? Dividing by that fraction is the same thing as multiply by the reciprocal. Multiply, distribute that through. So this is what your answer will look like if it was a multiple choice question. Okay. All right, so we made some progress. We've seen every type of problem that we can expect on the test for Tuesday. So tomorrow we'll start our trig unit, but we need the second half of the class to continue reviewing. Okay, if anyone's not going to be here, I have tomorrow. I have the trig unit packet